from a very simple principle. You can locate a device on the planet down to millimeters. You can buy a receiver and you provide the data into our cloud environment. We measure the quality. If you have high-rise buildings next to you, they're blocking part of the sky and you're not receiving. Availability, so how often are you online? And then we issue a reward depending on this. If you operate such an antenna on your roof, if this antenna would be moving by just half a centimeter, that motion will directly translate into an error in the application, because that device in the field depends on the stability of the antenna that you have.
Hello, everybody, to a new episode of How Does It Work? And today I'm super excited. I'm joined by Daniel from Onocoy. And Onocoy is building satellite position ground stations that make satellite image positioning more accurate. And today we're going to ask, how does it work? So Daniel, maybe you can give a quick intro, and then I have 3 questions for you today.
Sure. Hey, thanks for giving me the opportunity. Daniel here. I'm located in Zurich, Switzerland. My background is in GPS, so in satellite navigation. I've been there all of my career, which is now something like almost 30 years. Been doing a first startup in 1997, where we built the chips, so the actual electronics, which go into things like drones and autonomous cars and robotics, and IPO'd this company in 2007, reached unicorn status, 1.6 billion market cap. And it was quite a nice run, but now I'm focusing on high precision correction services, and that's the core of what we do at Onocoy.
Yeah. So how do these ground stations make the satellite positioning actually more secure? So more accurate? Like how I understand it is satellites are on a certain position and they always just send their time, right? So how do these ground stations make that more accurate?
Yes. So the satellites are orbiting the planet. So twice a day they pass by, and they, as you said, they send out a time signal that is being received by a receiver on the ground. And we can measure the reception time of that signal, and we know from the signal when it was sent. So we can determine the time of flight of that signal, and that signal passes through the atmosphere. And that's where the imprecision comes from, because the delay that the signal undergoes as it passes through the ionosphere, so the upper layers, and the troposphere, that is not known in advance. And that delay, that varies as a function of electron count in the ionosphere and as a function of essentially humidity in the troposphere. So in order to, if you want to make GPS more accurate, GPS and the other constellations like the European Galileo, the Russian GLONASS, the Chinese Beidou, if you want to make that more accurate and take it from 2 meters down to centimeters or even millimeters, you need to compensate for those errors in a real-time manner. And the way this works is you put up a reference station at a fixed location. That reference station receives the signals from the satellites, and because it knows where it is and because it knows where the satellites are, it can observe the errors on a per satellite basis and communicate that through a real-time streaming network to devices in the vicinity, say within 20 kilometers. And then those devices can locate themselves accurately by applying those errors, compensating the errors that they also observe. And that's in a nutshell how high precision works.
Do all these satellites have the same standard? Do they all send the same data signal?
No, the principle is the same. So they all send a time signal that can be received. But the receivers on the ground, they have, for each of the constellations, they're on different frequencies. They have different modulation schemes. They're different. But all the GPS satellites have the same way of transmitting. All the Galileo ones have different, but amongst themselves the same way and on different frequencies. So today on the ground, they're multi-constellation receivers. They typically receive all the constellations. So what you have in your phone receives satellites from all those constellations.
I see. So the ground station basically understands a signal from all the different satellites.
Correct.
And then they receive these signals. And since you have exactly the position where this ground station is, you have basically one more point that you can use to figure out more accurate where you are, because you're filtering out the cloud noise and so on from the atmosphere. Is that how it
works? More or less. So that ground station, that fixed station, we determine on an ongoing basis where precisely this is in millimeters. But the more important part is what current delays per satellite does this station observe. So for whatever GPS satellite 17 has 3.1 meters error as observed by that reference station. So the device in the field, your drone, can then compensate with these 3.1 meters and then have a more precise measurement directly to the satellite because it knows the guy next to me observed this and that error, so I can cancel it out.
I see. And then like I get a more accurate signal, right? Or an accurate position. And then Correct. I can use it, for example, to control a drone or a lawnmower or whatever.
Yes, exactly that. Right? So I mean, you've seen those drone fireworks where various drones, they work in concert and produce a pattern. And that's a typical application of high precision GPS. If this would be moving around with 2 to 3 meters, it wouldn't be the same show. Or robotics delivery on the ground, or also drones in the air, autonomous cars, autonomous vehicles in agriculture or in streets. That's where this is of high value.
Okay, cool. So, and how I understand it, that everyone can set up these stations themselves, right? And they get somehow incentivized for that by some kind of rewards on the Solana network, right?
That's correct.
How does this reward distribution work?
Yes, so you can buy a receiver which has that specific GPS-specific interface called N-Trip and provides the data to us. So that receiver has nothing proprietary in it. It isn't connected to the blockchain. It's a standard device that has been in existence. So these devices exist since 10, 15, 20 years. There's newer devices which are essentially cheaper than all the devices, but it's a standard thing. So it doesn't come from us. We don't earn anything on that. And you operate that device and you provide the data into our cloud environment. We measure the quality of the data, as in which constellations does it receive, which satellites does it receive. What is, for example, very important is that you have a full view of the sky, the satellite's orbit. So if you have high-rise buildings next to you, they're blocking part of the sky and you're not receiving. So we measure that. We also measure the availability, so how often or how much are you online on a 24-hour basis. And then we issue a reward depending on this. We also put into consideration the number of neighbors, because we don't want to have too dense networks. All we need is every 20 kilometers a station. So if there's too many people at the same spot, there's no added value for the network. And then there's a reward splitting happening. But up to 3 in the same spot, they can all earn the maximum. So we give back those tokens on a daily basis and in points at the moment on Solana. So we've been issuing points on Solana since probably close to 2 years now. And in the coming weeks, we're going to TGE. So we're going to switch from points to the actual token, the value appreciating token.
Mm-hmm. So, but how does it exactly work on Solana? So basically, these stations send their data to your backend, right? Correct. And then do you have some kind of oracle that has all these data so that your program can issue the rewards? Or do you every of these stations have their own like identifier, like a public key? Is it a key pair? Or how
that's the traditional interfacing that we're using. So there's those stations, they're configured with a username password that people can generate in our platform. That's how the device needs to be configured. We then identify those devices by the location where they are. So we calculate the position of those devices, and the user then needs to connect on our platform, needs to connect his device to his wallet, essentially to the chain. Mm-hmm. And once this is done, we issue rewards. And what we measure is what I just mentioned. We measure quality and sky visibility and various technical parameters. We publish then those values that we've determined out of the validation of, so the quality assurance essentially of the data on chain, which in turn then translates into the tokens that they get. Mm-hmm. So the actual data of the device is not going on chain, because it's like a real-time streaming network that we have. So the amount of data, that's not something that you want to have on chain.
I see. Yeah, putting data on chain is also very expensive. So basically, you have your backend, and then like daily or every few days, you go through all the accounts and you issue the rewards.
Correct. So the miners, they can claim on our portal, and yes, we accumulate the rewards, and once they claim, it goes into the wallet.
Mm-hmm. And these tokens is a normal SPL token, yeah? So everyone creates a new token account when they claim, and then at some point they can close it again if they want to move them somewhere else or they don't need it anymore.
Yes,
cool.
Correct.
Yeah, that sounds like a very good system. Mm-hmm. Then I have one more last question. So if I want to build one of these machines myself, so can I just use like an ESP32 and an antenna and put it on my roof and build it myself? Or
well, you're missing the most vital part in that. In principle, yes, you can build it yourselves because we are not a proprietary system. So you essentially don't need anything from us in order to contribute into the network. So no certificate or anything like that. But what you need is an antenna, which is something like this size that you need to put on your rooftop. You have a cable that runs into a GPS receiver. And that GPS receiver needs to be connected through some means to your home Wi-Fi or Ethernet. So yeah, people take ESP32s or Raspberry Pis. Mm-hmm. Then they connect a GPS receiver. Typically, such a receiver costs you somewhere between $100, maybe $50 to $200. It comes in the form of a USB dongle or a module that you solder. But there's also breakout boards that people have built. Mm-hmm. And that receiver needs to be configured to have the right messages. And then the ESP32, there is Docker images that you can load onto Raspberry Pi, but also for ESP32, there is software that you put onto it, which then needs to be configured to connect to us. Bill of material, probably somewhere $150 to $200. And yes, you need to do some soldering, you need to be familiar with Docker and such things, but it's perfectly doable, and the community also has developed many guides how to do that, how to build a device on your own.
I think that's super cool. I love this like permissionless, self-made system that you can just like build your own hardware and contribute to the network. I think that's super cool. And then I just would like sign up on your website and register my point somehow, and then you would do these checks in the back end if it's a real ground station, right?
Correct. And what we need to verify is if you provide data to us, we need to verify that this is genuine data, so that this actually comes from a physical device. And that's what we're doing in our validation internally. That's currently closed at the moment. That's centralized at the moment. We plan on decentralizing that. Yes, we need to verify that, and we can do so based on both spatial and temporal characteristics of the signals that your receiver collects.
Mm-hmm. Yeah, I mean, it's super important data. Like you said already, it's like used for drones and stuff. So yeah, you don't want.
There's many other things that we also need to do, as in quality assurance, because if you operate such an antenna on your roof, if this antenna would be moving by just half a centimeter, that motion would directly translate into an error in the application, because that device in the field, that drone, depends on the stability of the antenna that you have.
Of course.
So we're doing a lot of processing in the back end to do real-time monitoring of how stable is that, and if you put your antenna onto a long post, and that swings in the wind, that would be having a very negative impact. So behind the scenes, there's a lot going on in verifying the data quality.
So you probably also can't be on like skyscrapers or something, right? Because they also move like quite a bit.
That's correct. Yes, that's indeed a problem. They move due to wind, but they also move due to thermal expansion. So on a 24-hour basis, they actually move very slowly, which is another problem. So yes, ideally it's a low-rise building with perfect visibility of the sky. So your holiday home, for example, somewhere, that would be perfect.
That's cool. Do you have a live view, like where spots are that are not covered yet?
Yes, on our platform at console.onocoy.com, there's 3 views. One is the demand side view, so the people that can actually buy the data. So they want to see where do we have service. But there's also an opportunity map that you can switch to, which shows where have we reached saturation in the network and where is it still paying off to the maximum. If you would be putting a station there, there's also a marker that you can put on the map and see how much would you be earning if you would put up a station.
That's really cool. Yeah, thank you so much. So that's already my questions. Do you have any other things you want to point out? And we're going to put all the links probably. Yeah, I mean, you can talk a bit more if you have.
I could talk hours about GPS and how that works. I've been in that industry for 30 years, and it's a fascinating thing because from a very simple principle, you can locate a device on the planet down to millimeters. And the same principle works and operates since 30 years. That's why it's fascinating. But we can do a follow-up if there's further. But
I agree. I think even the idea is so amazing. Like just sending something up to orbit, and then it just sends the time, and you can do so much stuff with that.
Yes, and imagine the dimension. So if this were planet Earth, 6,000 kilometers diameter, these guys are 26,000 kilometers away. So it's like 2.5 times the Earth. So they're really far away compared to internet satellites that broadcast internet. And it's amazing that this technology works.
Oh, so these ones are further away. Yeah, that makes sense. There's like different orbits, right?
Correct.
So
your TV, your TV satellites, Sat TV, they're about 36,000 kilometers away. The GPS are 26,000 away. And everything, for example, Starlink, this is only a few hundred kilometers above us. So this is very close to the surface. Yes, they are far, far out. And the power that they send with is not much more than a light bulb. So imagine that light bulb 26,000 kilometers out in space. And we can receive it everywhere on the planet.
Yeah, because there's no clouds out there, right? But as soon as it gets in the atmosphere, it's more difficult, right?
Well, the clouds don't necessarily have an impact on receiving the signal. They do have an impact on the runtime of the signal. And that's what we compensate with Onocoy. So the clouds, especially if they are very humid, they do delay the signal slightly, which usually doesn't matter in your phone. But for high precision, it does matter.
Yeah, I mean, for a phone, it's like a few meters is usually enough, right?
Yes, indeed.
Yeah. Yeah, thank you so much. Like I could also talk for this about this probably for hours. Yeah, maybe we meet each other at some point at some DePIN conference. Like there's a bunch around the world, so I would love to.
Sure.
Yeah, thank you so much. I think it will be very helpful for all the Solana devs and the DePIN tinkerers, and maybe a few people will try it out. Maybe I build myself one.
Sure.
I think it sounds very interesting.
Join our Discord. People posted instructions how to do it, and they're very helpful. You can also just buy a box if you don't want to start soldering.
Okay.
So
that's maybe easy.
There's different companies who produce boxes that are affordable and can be used right out of the box.
Cool. Thank you so much, Daniel. That was amazing. And yeah, see you at the next one. I'll see you around at one of the Solana conferences, maybe.
Cool. Hey, it's great meeting you.
Bye-bye.
Bye.